Who's the next talk?
It's Fabrizio Sassi.
Fabrizio. I don't know. I guess we'll have to figure out. No, there was one other one. I'm sorry.
There are actually two, so we have two talks. The next talks for Fabrizio Sassi. They're going to tell us more on the NASA's development.
So this is more of a programmatic talk on what we plan to do at NASA Goddard. This is a project that we hope to start next fiscal year, and it's really a joint venture between the Heliophysics Division and the Earth Science Divisions under the Sciences and Exploration Directorate of Goddard. This is a combined effort of two laboratories, the GMAO, the Global Modeling and Assimilation Office under the Earth Science Division, and Stephen, who was here earlier, is the chief, and the Ionosphere, Thermosphere, and Mesosphere Laboratory, where I am, and I am the associate chief. Why this is? Why do we want to do this at NASA? First of all, the Science and Exploration Directorate is probably the largest Earth and space science research consortium or organization in the world, combining many different disciplines and crossing many different fields of research. More specifically, my division, the Heliophysics Science Division, provides an incredible suite of upper atmospheric observations, and my laboratory, the ITM Physics Laboratory, works to understand the complex coupling with the atmosphere below and space weather above. On the other hand of the campus is the NASA Earth Science Division, and they produce the GEOS model, the Goddard Earth Observing System. And we heard from Ricardo this morning some aspects of the GEOS configuration. And GEOS, more importantly, more specifically, why it is important is because through its analysis and predictions, it's able to capture the space-time atmospheric dynamics, which are really the most important aspect of the interactions between the lower atmosphere and the upper atmosphere, at least from a coupling from below. And also a vertical extension of GEOS. So the overall intention and the way we have pitched this project to management is that it will bring together heliophysics missions and observations, ITM physics, Earth modeling into the same analysis framework. And early on, we heard the conversations about how to integrate this. This is very important. And I want to emphasize that we could not do this project without the JEDI. So what are we interested more specifically in terms of altitude ranges? We are interested in what is called usually the space-atmosphere interaction region, which is the atmosphere, roughly speaking, from 50 kilometers to about 250, 300 kilometers. If you read up the literature, there are different definitions, but the original definition by Jeff Thayer is 50 to 250 kilometers. There are key science drivers that motivate us. Obviously, NASA is motivated by scientific curiosity, but also protection of assets in space and weather, space weather, and atmospheric weather interact in this very thin layer, the ITM region, the ionosphere, thermosphere, mesosphere. And they impact humans, they impact the economy, they impact society, as we heard from Tsuwei early on. But also the upper atmosphere affects the lower atmosphere. This is now well accepted. When 20 plus years ago, I was here developing the first version of WACAM, somebody told me that the atmosphere ends at 17 kilometers. But also we know that the climate response and the solar variability interact together. And really, we are in a world where we want these different disciplines to interact and make progresses together. If no other reason that we are in tough funding climate, and those fiscal considerations motivate us to work together to make things easier. And then finally, NASA is obviously in the business of sending things up in space. And so spacecraft orbiting and deorbiting is important. Somehow this is not the latest version, but that's okay. So the SARE is also an interesting region because in this region we have several observations. We have Time D that has been taking observations since the early 2000s. It's the longest record that we have for the upper atmosphere. Our MLS is still taking measurements, but we know that it's not going to last very long. Gold temperatures are very important, and they're still taking observations. But we also have ground-based meteor radars, and we heard today several talks about using wind observations in place of other observations that are now disappearing. And ground-based meteor radars they're not very many, but their record extends in time, back in time a lot. And then Icon Mighty was there for 3 years, but it is an incredible data set to be used. And in a month, I think, or 2 months, the EASY mission will launch. EASY is more interested in the electrojet, but they also will be observing winds, neutral winds, and they are very interested in having background atmospheric conditions to interpret their observations. Again, this is not the latest slide, but the green box was going to have only the main goal of GEOS MLT is to build a retrospective analysis of the mesosphere and low atmosphere for the past 20 years. So that's our main goal. We will leverage observations, models, analysis tools. We will advance the understanding of the SARE, the space atmosphere interaction region, and we can do this only with JEDI, covering many scales from short to medium and long time scales. So why NASA? The upper atmosphere clearly affects or rather the upper atmosphere and lower atmosphere are connected. The figure on the right-hand side is from a paper by Tom Immel of 2006, so almost 20 years old. And in that figure, you see the fingerprint of non-migrating tides, so meteorology that is generated in the lower atmosphere by convection, onto the ionospheric brightness. So this is one of the most clear example of how the lower atmosphere impacts the upper atmosphere. As I said several times, NASA is motivated by scientific curiosity and operational needs, satellite drag, climate change in the upper atmosphere, mission planning. I will talk about a couple of mission planning. We need to overcome silos thinking because progress can be made only when we integrate various different efforts. And the whole atmosphere, from my perspective, is a platform that can be used to bring together theory and observations. An example is exactly in the heliophysics domain, where people have taken many observations, but they're kind of in their own, they're kind of insular in their own domain. Instead, if we bring them together and we find a way to work them together, the entire field can make gigantic steps forward. So, but also the whole atmosphere is characterized by teleconnections. And the figure on the right-hand side is from a colleague of mine, former colleague of mine, Judith Lin. She's retired now. And it shows the typical structure of the mean meridional circulation in the whole atmosphere from the ground to the exobase. And you can see that it is, even if you draw some artificial boxes, as I've done, to identify, roughly speaking, the lower and the upper atmosphere, really, the atmosphere is a fluid continuum. And also we know that the upper atmospheric circulation matters to the lower atmosphere. An example is this paper that was published in 2011, in which they compared the skill scores of the same model with two gridings, two vertical grids, one that extends far high than the original one. And this shows the difference in skill scores from those two model simulations. And you can see that the skill scores are blue, so positive, even down into the lower atmosphere and to the troposphere. So this is an effort that we realize at NASA is an opportunity to integrate heliophysics mission data with meteorological observations using GEDI. Again, we could not do this without GEDI. But also it is a way or a conduit to the design, to help the design and concept of new NASA missions. And I will talk very briefly about two relevant missions, GDC and Dynamic. There are challenges. Forecast model errors and skills and their scale dependency in the upper atmosphere are not known. I think the upper atmosphere lags behind the tropospheric weather capabilities, or the way you guys do NWP predictions. They lag a lot. And the fact that we don't know how these model errors or skills are in the upper atmosphere is very disturbing. We also don't understand very well the wind dynamo coupling, and not just per se because it is important to drive, to generate forces that move ions with respect to neutrals, also because the conductivities that are underlying the wind dynamo coupling are important because there are currents that then close off in the E region, but they extend up high into the magnetosphere. And then there you go, you have not just a whole atmosphere, but you have a connection with the space weather. We need to identify cost and benefits of integrating helio mission data. I think Victoria was talking about the cost of running these simulations, the amount of GPUs that is required to integrate all these observations. And we needed to think of the integration with space weather drivers and space flight missions, because that is clearly the ultimate goal, even for NASA itself. So future missions. One mission that is in need of support of data simulations and OSSI in the upper atmosphere is the Geospatial Dynamic Constellation, GDC. Now, we are in an environment where fiscal prudency is very much necessary. So we don't know what, at the moment, as probably people have read on the newspapers, GDC has been defunded by the president's budget, but the Senate has reinstated the funding. So there are all these debates that happen in the Hill. But we think that GDC is a mission that was required by the community with the previous decadal survey. And so it should fly, and eventually it will fly. And the point of this mission is to take in situ observations of compositions of storm forcing, currents, aurora effect, wind flow. And in general, the science questions that this mission has is to understand the coupling between the high latitudes, thermosphere, ionosphere, and space weather, and how the internal processes that inherent to thermosphere and ionosphere affect those observations, those measurements. I'm not part of GDC, but instead I am part of one of the dynamic projects. We are 3 teams in phase A competing to move forward. Some of the folks are in this room as well. I'm with the Scott Bailey team at Virginia Tech. And so I'm showing this slide, of course, I'm advertising my own team. But in general, regardless of which slide I show from which team, and whichever team will win eventually, the goal of the dynamic mission is to provide more observations in the data poor region of between 100 and 200 kilometers. Now, if you go to the different teams, there are different types of measurements that are taken, and I'm not going to dwell into that. But the main science questions that are part of this mission, this future mission, is to understand how atmospheric variability affect the Earth weather affects the thermosphere and ionosphere, and how the thermosphere responds to geomagnetic impacts at high latitudes. This mission is very much tied with the GDC. In fact, the risk is that if GDC is canceled, dynamic will be canceled as well. And then we won't have any observations in the thermosphere for sure for the next 15, 20 years, because these 2 missions are scheduled to fly probably late 2020s or early 2030s. If they're canceled, there is nothing in the books now for another mission. So we are really data starved. What are we going to do at our end, gathered to do this? As I said, the main goal of this GSMLT is to produce a retrospective analysis for the past 20, 25 years. So this is sort of a laundry list of the observations that we wanted to use. We already heard about SABRE that Ricardo has integrated with the GSI, and then we want to use also wind observations for the reasons that are available. I understand, and everybody probably understands the difficulty of using wind observations in data simulations, but they are there. And to be honest, if the space flight emissions do not happen, that's the only thing we have to know what is the state of the thermosphere and the ionosphere. AW is flying now, so they are taking observations of temperature, and whenever they release their data, I think it's an incredible data set that will be available to the community. But again, this is only at 80 or 90 kilometers altitude. GOLD, ICON, AIM, SOFI, and this probably is not going to be all the data sets that we are going to use. Probably we will end up not using all of these, but this is sort of what is in my brain, or what we can use and what we probably should be using if we want really to develop a system that is able to interpret the upper atmosphere. So briefly, again, this is not the slide set that I was planning to show, but in any case, this is the development plan that we have, and I apologize for the weird fonts on the left-hand side. We started with the GEOS that is valid up to about 60 kilometers, because that's where they stop ingesting MLS temperature. And again, apologies for the bad fonts, which I thought I had fixed. The GSMLT is going to extend to about 150 kilometers. We want to use all those observations that I listed in the previous table. And again, the goal is to create a climate record from the ground to the lower thermosphere. Think of it as a MERA-2 on steroids. MERA-2 stops at about 60 kilometers. We want to have a ground to, say, about 150 kilometers. And when I say, and I wave my Italian hands a lot, because really where we put the lead will depend a lot on what the model configuration, what stable model configuration we will get. But I think we should be able to get at least to 150 kilometers. Okay, so this there was another slide that is not in this set, but that's okay. I was going to say that to show a slide is similar to what Ricardo has shown this morning. And the idea is that we are trying to keep this project funded that we started in FY24 with internal funding gathered. And we are moving forward with hopefully funding in FY25 for the next 3 years. And our aspirational goal is to go to whole atmosphere coupling. So coupling with the space weather and the ionosphere. So as I said, the NASA prioritizes scientific discoveries, space flight mission planning, protection of humans and assets in space. NASA is not in the business of forecasts. NASA GMAO has provided for many years through GEOS a framework for integration of a very diverse set of Earth observations with numerical models. So it's very natural that we work together. And ITM, my laboratory, brings together all these observations that we are going to be using. As a matter of fact, the project scientist of GDC is Doug Rowland, who is in our lab. So that's another reason why we want this mission to fly. If anything you want to stick in your head after my talk is that JEDI is a key enabling tool for this project. And we couldn't do it without the work that you guys have done. Also, this project is new. Hopefully, we will hear in the next couple of weeks that we are funded. So I encourage young people to think about what they want to do and get in touch with me if you're interested. Other than that, thank you.
Thanks, Fabrizio. Question at the end? Since we, yeah. I think we're a lot of data questions, especially you're bringing a lot of neutral density, neutral wind, that data in this. Last talk in this session is Eric Sutton. Eric's going to talk about his work with satellite, using commercial satellites to derive the density.
Yep, thank you. Yeah, nice to see everyone here. Thanks for having me. I'm just gonna kind of go over a few data sets that are out there that are at least in my sphere of knowledge. And specifically, I'm going to be looking at things that are coming from constellations. But I thought, maybe before I move on to the next slide, I could give kind of a preface to this in terms of thermospheric densities or data relating to the thermosphere. This I think measurement of the thermosphere really started in earnest in kind of the late 50s and 60s as people began tracking satellites with ground-based radar systems, and that technology lives on today through the DoD's program to track a handful of objects, about 90 or 100 objects, that they then feed into the HASDA model, which is the high accuracy satellite drag model. That's kind of the operational thermospheric model for the DoD. This is a kind of a protected model, so not a lot of, for instance, commercial constellation owners can use it. That's anyway, the tracking is one data set that's been out there. In the 60s and 70s, they started developing accelerometers and mass spectrometers that they could send up and get things like a total mass density for the accelerometers, or a chemical composition, temperature, and even sometimes winds from mass spectrometers. The heyday for those was really in the 70s and 80s. And in the last 40 years, we have not flown, to my knowledge, a single successful mass spectrometer in the thermosphere here at Earth, but the state of the art has lived on in missions like MAVEN at Mars and other planetary missions like that. In the kind of the modern era of the accelerometers, started in the early 2000s with the CHAMP satellite and the GRACE satellite, and Goche and to some extent Swarm, and what's flying right now is GRACE follow-on. So these are Earth science geodesy missions that the thermosphere community has been able to leverage. But this is kind of the landscape of thermospheric measurements, and so we've tried to find what we kind of